Namaste students. Today we are going to start with the next topic of class 11th, that is principle of mathematical induction. Principle of mathematical induction. What exactly it is? See, in mathematical discussions, to reach to a scientific conclusion, we use two methods of reasoning. One is method of deduction and the other is method of induction. Method of deduction and the second is method of induction. Now let's see what exactly these are. If I talk about the first method, that is method of deduction. In method of deduction, actually, we go from general to particular conclusion. We move from general to particular solution. Means it's a generalized thing और वहाँ से we go to a particular solution, conclusion. For example, I'll give you an example. Say we say all the digits having 0 or 5 at the unit place are divisible by 5. All the digits having 0 or 5 at the unit place are divisible by 5. Clear? It means this is a general result. All the digits having 0 or 5 at the unit place are divisible by 5. Now I come to a particular conclusion that 365 is divisible by 5 because it has 5 at unit place. It has 5 at unit place. Is it clear? Method of deduction is clear to you all? Method of deduction means I have a journal result. From that journal result, we come to a particular result. From journal result, we come to a particular result. Method of deduction is from journal to particular. From journal to particular. Okay, let's talk about method of induction. Method of induction, which actually is our topic. Clear? Which is our topic. Method of induction. Now, in method of induction, what we do or what happens, it is from particular conclusion to a general conclusion. In method of induction, we move from particular to general. We move from particular to general. Is it clear? Alright. For example, if I take an example that 84 is divisible by 2. 84 is divisible by 2. Fine. Now I say 84 is divisible by 2. It's a particular case. If I try to generalize this result by saying so, it means all the digits having 4 at unit place are divisible by 2. See, this was a particular result 84 and I generalize according to me. This is my perception. See, I say somebody is saying 84 is divisible by 2, then I'll say, okay, it means all the digits, all the numbers which has 4 at the unit place will be divisible by 2. That's my perception. Is it clear? I am generalizing it in my own way. But that's not actually true. So if somebody can say, maybe somebody is saying, okay, according to me, maybe you're trying to say that all 2-digit numbers are divisible by are divisible by 2. Is it true? No, it's not true. If I say example, say 57 is not divisible by 2. It means there's a problem in this method. If I say from particular to general, if I'm saying 84 is divisible by 2, my perception is because it has 4 at the unit place, so it is divisible by 2. It means all the numbers having 4 at the unit place would be divisible by 2. That's my perception. But somebody else comes and says, no, my perception about it, all the 2-digit numbers are divisible by 2. But that's not true. So that means if I am going to drive some journal conclusion out of a particular solution, that is just a or you say conjecture, or I say just a guesswork. It is a guesswork. It is just a guesswork. Is it clear? It is just a guesswork. It is not fixed that actually it is true. It is just a guesswork. Alright? Now, but we can't work on a guesswork. We can't just assume the things on our own and we start doing the method. So what do I need to do? Unless I don't support my statement with some reasoning, with some scientific method, these are only conjectures. These are only conjecture. Is it clear? These are just guesswork, nothing else. These are just guesswork. So we will not work on guesswork. So what we have done, we have derived a method. There is a method that is called principle of mathematical induction, which is called principle of mathematical induction. Through this method, first of all, we come to a guesswork. Is it clear? We come to a conjecture. Then we support it by proper steps. Then we prove, yes, whatever is the particular solution, that solution or that conclusion can be generalized. That conclusion can be generalized. Alright? Okay. Now, I told you, from a particular solution to generalize the conclusion, we have to give a scientific reason for it. Alright, there should be a solid support to that. So for that, there is a method, the principle of mathematical induction. This principle indicates that if Pn is a statement, including natural numbers, then number one, P1 is true, that is Pn is true for n is equals to 1. That means that whatever the statement is given to me, is it clear? Whatever the statement is given to me, that is always true for n is equals to 1. That means in place of n, if I put 1, the statement is true. The statement is true. Then these things will be more clear when we'll do the practical questions. Alright. So our first, you say the first statement, what does this principle indicate? The P1 is true. That means Pn is true for n is equals to 1. Second is Pk plus 1 is true whenever pk is true. What does it mean? What does it mean? pk plus 1 is true whenever pk is true. That means the truth of pk implies that pk plus 1 is true. Is it clear? Alright girls. So what are we doing? P1 is true. That means if I put n is equals to 1, the given statement is true. Then pk plus 1 is true whenever pk is true. That means we assume that pk is true, and for that we prove that pk plus 1 is also true. We assume that pk is true, and for that we prove that pk plus 1 is true. If these two, rather three we can say, we can write down the steps after that. Alright, if these are true, then we say therefore the given statement Pn is true for all natural numbers. Is true for all natural numbers. Is it clear? Alright students, fine. So this principle indicates that any statement which is given to you, first of all, that should be true for n is equals to 1. That should be true for n is equals to 1. These are the steps of working also. First of all, I'll prove the statement true for n is equals to 1. Then I'll assume that the statement is true for n is equals to k, and I will prove that the statement is true for n is equals to k plus 1. If this exists, then we say the given statement is true for every natural number. The given statement is true for every natural number. Alright, fine. I'll just give you an example how it is happening. Suppose you have to climb a ladder. You have to climb a ladder. There's a ladder. If you are able to climb on the first step, that is my step 1. If you are able to climb on the step 1, the same way you will climb on the step 2, same way you will climb on the step 3, and so on. Is it clear? So that means I will prove the result first of all for n is equals to 1, that whether I am able to climb on the first step or not. Clear? Then we go further. Then I am assuming I am able to climb at step k. Is it clear? So suppose if I have started from here, I am able to climb here, and same way I will be able to climb on 2, 3, 4, 5. So I am able to climb at sk. Then I will prove that I am able to climb at this step also. Is it clear? This is the working of mathematical induction, which we are going to support now with the examples. We are going to support with this method with an example. Alright, we'll do different kind of questions. Alright, there are 3 types of questions which we'll be covering. First, statements, divisibility and inequalities. That's what we are going to prove in this topic.